Okay. So now that we know that f of x plus f of y equals to f of xy, then that means I can also say that the next line would be, if I have log e of x minus log e of y, this is the same thing as writing f of x minus f of y equals to f of x on y. Okay, because that's all I'm doing. I'm just replacing the xy, the y, and the x into what the function I've defined. Now you'll be like, yeah, I sort of knew that, sir. Like f of 1, and you know that you sub 1 in. F of 2, you know you sub 2 in. I know, I said it's an easy concept. It's when you apply it into an exam question, you're trying to find your A, B, C, D, E, which one is your correct answer. You'll have to play around with the equation until you get your answer, until you get the correct one. And it's hard because this is an interpretation skill. And so it's hard to apply it in your calculator. Even if you had a calculator, it's hard to solve. That's why it's a tricky question. Okay? Now, let's take another example, just so you get used to the idea here. You can have f of x equals e to the power of x, and I can then say e to the power of x plus y. You see, I want you to see that all I'm replacing right here is I'm replacing the x plus y with the x. So that means I can rewrite that in terms of my index laws. I can rewrite this as e to the power of x times e to the power of y. This is index law 1. When you times two indices with the same base, you add the powers, right? So it's like if I had a to the power of 2 times a to the power of 3, you'd say that's a to the power of 2 plus 3. So all I'm saying is e to the power of x times e to the power of y is the same thing as writing e to the power of x plus y, right? Now that means if I've replaced this, if I said let f of x equal to e to the power of x, then this is the same thing as saying f of x multiplied to f of y, because I'm replacing the x with a y, and this is just f of x plus y. Okay, so I'm trying to show you that notation, how we're using function notation to represent our expressions or equations. Okay, so if that is true, oh, I actually gave you the answer. I forgot to animate that. It was meant to be your turn to do this one. All right, well, if you had to look at this question, f of x equals to 1 on x, so I'm just replacing this as my f of x. I was asking you to verify that f of x plus f of y is equal to this. I've shown the algebra here. So f of x, which is here, f of y, which is here. I'm just replacing the x and y's. And I wanted to simplify this to prove that this is true. So all I did was I made the denominators the same. Okay, so I times this by y, times this by y, times this by x, times this by x. That gives me a denominator of x and y. So that means I've now got y plus x with the same denominators. That's collecting it together. But at the same time, I can rewrite this as taking 1 on x, y out multiplied to y plus x, which is exactly what this is. But conveniently, 1 on xy is exactly the same thing as writing f of xy. Because this is what I said. I said that f of x equals to 1 on x. All I'm replacing is the xy. So I've proven that yes, f of x plus fy is actually f of xy times x plus y. Okay? And that's the method. Now, what you can see here is what was the tricky part? What made it feel different and what made it feel hard is to get the idea that what you defined at the start is a replacement for y. Okay, and that's the tricky part, because what I've just taken you through is simple algebra. Okay, but it's the interpretation to get your answer to what you want. And that's exactly what we're going to do in the next slide. I've got 2 questions for past exams, and I want you to do the same thing. Try to interpret it as what you're doing here. You're just replacing the defined function, replacing that x. And if you can do that, you can do the answer to those 2 questions. Okay, you don't need a calculator. Maybe for the second one, you can use a calculator. But for the first one, I don't want you to use a calculator. Okay, so for both of them, there were about a 42% and 47% of the state that you got it correct. Okay, so once you understand this concept, I want you to try these 2 questions, okay? Have a go with these. These are 2008 and 2007, so it's more relevant to your year now. And there's one almost in every year, so I can find one in 2005, 2004 as well. This is a typical one to come up once. So if you have a look at question 12, it's exactly the same technique to use your function notation to interpret and find which one's your answer. And this one you can use a calculator if you wish, or you can do it by hand. Calculator will make it faster. Okay? I want you to have a go with these two, and I'll show you the answers to them. And then the last one, which is 2007, the very last question, I thought that was a very nice one. It really tests how much you understood in my last lesson about composite functions. Okay, if you really understood, you should be able to tell that answer from the last question. Otherwise, start off with these two. And then once you finish those three past exams, I want you to have a go with this. It goes back to inverse functions and functions, domain, range, implied domain, all in one. They always have it every year. It's the same thing over and over. Okay? I reckon I'll give you maybe 4 minutes. I'll give you a maximum of 2 minutes each. Okay? That's 150. If you didn't want to do calculator for question 17, do process of elimination first, because logically you can eliminate half of it out already. There should only be about 2 or so that you're just deciding on. Then you can use algebra if you don't want to use a calculator. We've got a minute left. Time's up. Can I get a quick show of hands who were definite that they got the answer correct for 2008, question 12? Okay, that's about the same, kind of about a third of you. That's all right, that's about 30-something%. And then what about question 2, who's definitely sure that they got this one correct? Okay, again, about a third. Okay, cool. Excellent. Oh, a bit less than a third. That's good. This is what I wanted to challenge you in terms of the idea. It's a simple concept, but it feels hard when you're in an exam to do this, especially if you're giving yourself, I gave you 2 minutes to do it, which you should take shorter. You don't want to take longer than a minute and a half. But here we go. So if we have a look at the first one, especially if this came up in your exam, my first tip is look at your multiple choice questions. Okay, your multiple choice, because you have to select one of them, they give you hints on where to start. You see, for me, as soon as I saw this, in my mind, I was thinking, all right, so f of 2u means I'm going to replace all the x's with the 2u. So what you should have got is this is what you're looking for. You've got e to the power of 2u plus e to the power of negative 2u. True? Okay, so everyone would have started off there. But the question is, well, none of those seem to show it. But at the same time, you also can eliminate some answers as well. For example, the first one, f of u plus f of negative u is technically the same thing as the equation just replaced with a u. So it clearly cannot be the answer, because this would have been e to the power of u plus e to the negative u. That is no way in any way near what we want. So we could already eliminate that, and we can eliminate a and b, because 2 of f of u just means you're multiplying 2 to the function. So that doesn't make a difference. Okay, so I already know straight off the bat that a and b wasn't the correct answer. The only problem now is it has to be c, d, or e. Now what's common about them all is they all have f of u squared. So the question is, what is f of u squared? What does that equal to? That is what I meant by your multiple choice questions or parts will give you hints on where to start. So my first question is, okay, well, what does f of u all squared actually equal to? Well, we know f of u was e to the power of u plus e to the power of negative u squared. This is actually just quadratics. Yeah? You've got a plus b squared, so if you square it, square the first one, square the last one, and then multiply 2 to every term inside. So if I square the first one, it makes sense that this will actually give you e to the power of 2u. Square the last one, it makes sense to give you e to the power of negative 2u, which is actually very similar to what I have up here. The only difference is you had to multiply 2 times a and b. And this is, in this case, I've got a as e to the power of u and b as e negative u. So it actually becomes e to the power of u multiplied to e to the power of negative u. Now we know from index laws that when you multiply with the same bases, you add the powers. Now u plus the negative u makes it 0. E to the power of 0 is 1. So what this is actually saying is f of u squared is actually equal to e to the power of 2u plus e to the power of negative 2u plus 2. But what we wanted was just e to the power of 2u plus e to the power of negative 2u. What I don't want is a plus 2. So the only way to get rid of it is if you had f of u squared minus 2. Because if you minus the 2, you lose that. And if you lose this, they're both the same. So the answer should have been C. Okay, so in terms of the guidance, what I did, I was just applying what we've learnt. F of 2u just means replacement, but I'm looking at my solutions, I'm like, no, a and b can't be it. It has to be either c, d, or e. And then I use the guidance of f of u squared to get my answer. Okay? Now, for the second one is by the same concept as well. You see, you're saying this is a composite function. This is just saying I want to sub itself into itself. Okay? And I said that from here you can already eliminate half of the solutions, because logically, if this is x plus 1 and I sub x plus 1 where x is, then I end up with x plus 1 and I sub x plus 1 in, then I just get x plus 1 plus 1. How is that going to cancel out? Because logically I'm just replacing it with an extra plus 1. So logically, that can't cancel out in any way. And same thing if I put it in here, it will just be another minus 1. So already a and b can't be the answer. I don't know about x minus 1. Maybe if you divide, something might cancel out. But I know d can't be it, because if I replace x with a log e of x, you technically got log e of x of log e of x. How does that work out? So log e of x, you can't cancel that out. So you know that b, and a are out of the equation. The only thing you're skeptical about is whether c and e is correct. So if you had to do it algebraically, you're just testing, what if I sub x as its own function? So you have either x minus 1 on x plus 1 minus 1 all over x minus 1 on x plus 1 plus 1. And you can do this algebraically because minus 1 and plus 1, you can rewrite that as x minus 1 on x plus 1 minus x plus 1 on x plus 1. Keep the same denominators, and it's the same thing on this one. You could have x minus 1 on x plus 1 plus x plus 1 on x plus 1. Okay, and you can cancel that out and play around. So you know that adding the denominators, that will cancel out, these two will cancel out, and then you can solve from there. And then you can test the two, see if they're both equal to what we want, which is x. Alternatively, the method I approached was, because I knew the answer was either C or D, if these were my two answers, C or D, all I did was I plugged into the calculator, because I just wanted to solve which one of those is true. So all I did, which I'm just going to remove this so you can see, because I knew what I needed to define, and there was only two of them that potentially could be the answer, all I did was I said, define f of x is this, and I said, solve if I sub f of x into f of x and I want it to equal to x. Solve for x. If it's true, then I've got it. I pressed enter, it said false. I'm like, okay, so it can't be that one. Let's test the next one. And I started doing the same thing. I redefined it, I just changed the signs. And I sub it in, and it comes out as true. So I know the answer has to be E. Or alternatively, you could have done the algebraic way, but in an exam, I would have used the calculator for that, just to get it over and done with. Too many fractions, I might make a mistake.
Could you also do it since it's function of x, therefore function of x is equal to the inverse function of x? And then you could do it graphically.
Oh, I see what you're doing. You're saying, wait, say that inverse part again, just to make sure that I'm understanding what you're saying.
So, function of the function of x equals x, and then you do inverse function for both sides, so it's fx equals inverse function of x.
Oh, and then you graph the inverse, but yes, but which function would you sketch though?
Well,
Oh, okay, and then you do the inverse and find where they point.
yeah, and then the same.
Yes, I think you can. I just think it will be a bit more tedious because you have to find the inverse function to it. What would that be? Unless you can do it on your calculator to find the inverse, then it might be quicker. Yeah, I think that would work if you can do the inverse. Then it should show where the point of intersection is. Okay, now, just to show you the stats on that one, this is the examiner's approach if you want to see how they did it algebraically. But 40%, 47% on question 17 and 44%, I thought it was worthwhile. If you're wondering what the ones are, that's just 1% of the state leaving it blank as they're not answering the question at the very end. So this section here, okay, number of questions that they, or number of percentage of number of students who left it blank that year. So it's generally 1% anyway, because if they're in doubt, just guess, yeah? In our case, you would have noticed we generally eliminated down to 2 possible solutions before you make a solution. So you can have a 50-50 guess most of the time. All right. Now, those are the 2 that I thought was interesting. Now, the next one that I'm going to give to you is unrelated to the function notation, but it is more related to composite functions. That one was 37%, so it's much harder than this idea, but the concept is still straightforward. If you understood what I said in the last session about composite functions, being the range of your function being the subset of the next one, you should be able to answer this question in less than 10 seconds. But if you can't, otherwise it's going to take longer. Okay, so have a go with this question. It's 2007, the last question of 2007. I'll try to squish it all in one point, so hopefully you can see it. You've got graphs of f of x, you've got g of x. So you can think of f of x being a parabola, and you can think of g of x being a modulus x graph. They want you to find f of g is best represented by which of these graphs here? Have a go. You can use the calculator if you wish, but you don't need to. You just need to understand the concept that I talked about in the last session, and you should be able to answer this. So I'm going to give you 2 minutes. Have a think. So it's 2:02 now. You have 2 minutes to have a think, and then I'll explain it to you.
No, I made a mistake that year. There's no answer.
All right, let's have a look. 37%. Let's see how many of you got this correct. Hands up if you got your answer as A. It's okay, you never know, you might be the one and out of 60 correct. B. All right, 1, 2, 3, 4, 5. Okay, cool. That's about 1/12 of you. What about C? 1. D? E? Oh, that's interesting. So that's about, that's a good, close to a third. So, the answer, which I'll tell you as I explain it, why you can eliminate certain answers. So it's good that no one chose C, but if you didn't choose C, that also means that you shouldn't have chosen B. Now why? Why do you not choose C and why don't you choose B? Now remember the concept I said f of x, a composite function. I said yesterday, or in the last lesson, I said that g of x is your range of g. So regardless of what f of x is, which we know is a quadratic. So this is all I'm saying. I've just got a quadratic, I squared it, right? And the idea is the range, what I'm substituting is my modulus function. Now notice that the modulus function, the range is -infinity to 0. So that means that every time you sub a number in, every time you sub a number into this quadratic, it is always going to be a negative number. So if you look at the original graph, which I'm going to highlight so you can see, if I just highlight the original graph, this is my original graph. This is based on numbers, based on positive numbers on your right-hand side, based on negative numbers. Now, if I told you from your range that all I'm substituting in is going to be negative, then that means on the left-hand side, the negative side will always be as itself. It hasn't changed. I'm just putting a negative number. Okay, so that means it always has to be on the positive. It has to be above the x-axis. It can't be below the x-axis because right now, when x is negative, your graph of f of x is always positive. So regardless, I'm always substituting a range of negative numbers. That's all I'm doing. I'm always putting in negative numbers into the function. So of course, it has to be above the x-axis. It wouldn't have been C or B because it's gone below the axis, and there's no chance of it going below the x-axis. The next thing that you can eliminate, which is D, why can you eliminate D? Now, composite functions, if we think about it logically then, that means whatever you're substituting in, you know, that's what you're putting into the equation. Now, the one spot that you can look at is right at the center. Both of those functions, when g of x, g of 0, it's equal to 0. And so if I sub f of 0, of course it equals to 0 because the original function was 0. If you sub 0 in, it's meant to equal to 0. And it's true. So that means that at least in this composite function, the one thing we know is that it has to have a coordinate right at the origin. So it can't be this one because it doesn't have a coordinate at the origin. That doesn't make sense because you're saying at x equals 0 in both graphs, it's 0. So of course the composite function has to end up being 0. Okay? So it can't be B, it can't be C or D. Now you're going back to, it's either A or E. Now if you understood that one concept that I said that you're just substituting a range and it's all negative, notice that this is symmetrical. It doesn't matter what this y value is. If I call this y1, this is still y1. So that means when I sub it in both left and right of this composite function, it should be exactly the same. Because I'm substituting only negative numbers. And if it was -1, then in both cases, I'm still subbing in -1. So you should have a symmetrical look on both sides. So that's why this can't be the answer. And E is the answer because that is the only one that's symmetrical when you're only substituting two negative numbers. Okay, if that makes sense. Yeah, so the answer is E for those. Excellent. Now that concludes today's session in terms of function notation. I do want you to have a look. I've put two more questions with. There are two more questions in here with function notation. So it was question 9 and question 17 on the back page. Those are your function notation related to today's session. Have a go with the sheet. I do want you to do them and we'll write the solutions for every of the past exams. Now, if you didn't know, in Schoology, I've now made a separate folder and it says VCA exam questions. And you know, when I'm free, I'll just go through 2002 to 2015 and I'll select questions based on topics. So there's so far revision for functions and inverses, sheet 1, which you got yesterday, and then functions of revision inverses, sheet 2, and you got a general functions as well. So as we keep going through, I'll keep selecting questions that I think is related to functions, and I'll collect it all. So it's like I'm doing a checkpoints thing for you. Okay, I'm just choosing all the questions I think is related to functions, so you can revise if you want to. Okay, so please have a look at that on Schoology. Otherwise, in this session, please work on this, and then before about 5 minutes, that's when you can leave. So maybe another 5 minutes, then you can leave. Okay, I'm going to pause the video.